Hello friend, welcome to Math A to Z. Our today's topic is very important theorem of sequence of real number named Cauchy's second limit theorem, which state that if xn be a sequence of positive term and limit n tends to infinity, xn plus 1 by xn equal to L, and L is finite or infinite, then limit n tends to infinity, xn to the power 1 by n equal to L. This is the statement of Cauchy's second limit theorem. Now we prove this theorem in three parts, that is in three cases. Now come to the case number 1. In the first case, we take limit n tends to infinity, xn plus 1 by xn equal to L, which is finite but not equal to 0. So from the definition of limit of a sequence, for any epsilon greater than 0, there exists m belongs to capital N such that mod of xn plus 1 by xn minus L less than epsilon for all n greater or equal to m. Now expanding this, we get L minus epsilon less than xn plus 1 by xn less than L plus epsilon for all n greater or equal to m. So if we put n equal to m plus 1, m plus 2 to n minus 1, then the above relation satisfied. Now putting this value of n in this relation, we get, here we take epsilon by 2, then here epsilon by 2 and epsilon by 2. Now putting n equal to m, we get L minus epsilon by 2 less than xm plus 1 by xm less than L plus epsilon by 2. L minus epsilon by 2 less than xm plus 2 by xm plus 1 less than L plus epsilon by 2. And in this way, we get L minus epsilon by 2 less than x n by xn minus 1 less than L plus epsilon by 2. Now if we multiply vertically all the result, we get L minus epsilon by 2 less than L plus epsilon by 2, and there is n minus 1 minus m plus 1, that is n minus m number of relation. So to the power n minus m and to the power n minus m. And when we multiply vertically, then there is only two terms, xn by xm, and other term can be cancelled, xn by xm. Okay, we name this as 1. Now if we consider first and second part, then we get L minus epsilon by 2 less than xn by xm all to the power m and here to the power n. Now this is not correct. We get L minus epsilon by 2 to the power m less than xn by xm into L to the power m, because L minus epsilon by 2 less than L. So we can write from this to this. Similarly, if we choose second and third portion, then we get L plus epsilon by 2 whole to the power n greater than xn by xm into L plus epsilon by 2 whole to into L plus epsilon by 2 to the power n, and this greater than to the power n, and this greater than xn by xm into L to the power m. Okay, this is 2 and this is 3. Now from 2 and 3 we get 2 and 3 we get 2 and 3 we get L minus epsilon by 2 whole to the power n less than xn by xm into L to the power n, and from here to here that is less than L plus epsilon by 2 to the power n, imply xm by L to the power m into L minus epsilon by 2 less than xn less than L plus epsilon by 2 to the power n into xm by L to the power n, L to the power m. Now taking nth root to the power 1 by n, here to the power 1 by n, here to the power 1 by n, and here n to the power 1 by n cancel, here also n to the power 1 by n cancel, this is to the power 1 by n, and this is named as question number 4. Here xm by L to the power m is a fixed number. Xm by L to the power m is a fixed number. Xm by L to the power m, this is a fixed number. So to the power 1 by n tends to 1 as n tends to infinity, tends to 1 as n tends to infinity. So this side tends to L plus epsilon by 2 and this side tends to L minus epsilon by 2, right? This side, since this is tends to 1, so this side tends to L plus epsilon by 2, and since this is tends to 1, this side is also tends to L minus epsilon by 2. Now since L plus epsilon by 2 into xm by L to the power m to the power 1 by n tends to L plus epsilon by 2 as n tends to infinity. So and also L minus epsilon by 2 into xm by L to the power m to the power 1 by n tends to L minus epsilon by 2 as n tends to infinity. So we can write L plus epsilon by 2 minus epsilon by 2 less than L plus epsilon by 2 into xm by L to the power m to the power 1 by n less than L plus epsilon by 2 plus epsilon by 2, and L minus epsilon by 2 less than L minus epsilon by 2 into xm by L to the power m to the power 1 by n less than L minus epsilon by 2 plus epsilon by 2. And for both the limit there must exist k belongs to capital N such that for all n greater equal to k and for all n greater equal to k. Now calculating them we get here this side only L and this side L plus epsilon. Also here this side L minus epsilon and this side only L. Okay, and these two relations we named as 4 and 5. Now start from 5 we get L minus epsilon less than xm by L to the power m to the power 1 by n into L minus epsilon by 2. This less than xn to the power 1 by n, and this can be proved earlier. Xn to the power 1 by n less than this also can be proved earlier. Xm by L to the power n to the power 1 by n into L plus epsilon by 2. And now we take this side L plus epsilon by 2 for all n greater equal to k. Sorry, L plus epsilon. This is not epsilon by 2. That is, we get L minus epsilon less than xn to the power 1 by n less than L plus epsilon for all n greater equal to k. So we can write the result mod of xn to the power 1 by n minus L less than epsilon for all n greater equal to k. That is limit n tends to infinity xn to the power 1 by n equal to L. So we say that xn to the power 1 by n tends to L also, where L is finite but not equal to 0. This is the proof of the first case. Now we go to the second case. Case 2. Go to the second case. Let limit n tends to infinity xn plus 1 by xn equal to infinity. This is infinity. So there exists m belongs to capital N such that xn plus 1 by xn greater than 2g for all n greater equal to m, where g greater than 0 being however large number. Here also we put n equal to m plus 1, m plus 2 dot dot n minus 1. Then we get xn plus 1 by xn greater than 2g, xn plus 2 by xn plus 1 greater than 2g, and at last xn by xn minus 1 greater than 2g. Here multiplying all this result vertically, we get xn by xn greater than 2g to the power, the number of relation is n minus 1 minus m plus 1, that is n minus m relation, n minus m, imply xn greater than 2g to the power n into xm by 2g to the power m. Now xn to the power 1 by n greater than 2g into xm by 2g to the power m whole to the power 1 by n. Here also xm by 2g to the power m is a fixed number, fixed real number. So to the power 1 by n tends to 1 as n tends to infinity. So we can make xm by 2g to the power m whole to the power 1 by n greater than half for all n greater than equal to k. Then using this result, we get from this result as xn to the power 1 by n, xn to the power 1 by n greater than 2g into half for all n greater than equal to m. That is xn to the power 1 by n greater than g for all n greater than equal to m. So this is the definition of divergent sequence, diverge to infinity. So we can write limit n tends to infinity xn to the power 1 by n equal to infinity. So this is the proof of second case. Now remaining one part in which this is equal to 0. This is case 3. Here if we put yn equal to 1 by xn, yn equal to 1 by xn, then this case convert to case 2. Then we say that using case 2, limit limit n tends to infinity xn to the power 1 by n equal to 0. So this is the proof of third case, and this completes the theorem, which is Cauchy's second limit theorem. Discuss about the converse of this theorem. Is the converse of this theorem is true? In this theorem, we say that if this limit is L, then this theorem proves, or this theorem gives, this limit is also L. Is that true? If this hold, then this also be hold. So we go to the converse of the theorem. Converse of the theorem. We say that the converse of this theorem may not true, because we consider an example. We consider a sequence as 1 a b, a square b, a square b square, a to the power n minus 1, b to the power n, a to the power n, b to the power n. Continue. Here a not equal to b. We see that the ratio tends to a or tends to b. This is variable. This by this is equal to a, but this by this is equal to b. So this is not convergent. This is oscillate between a and b. But here xn to the power 1 by n tends to a, as n tends to infinity. So we say that this is convergent, and we get the limit L as AB, but this is not convergent. So the converse of the Cauchy's second limit theorem is not true. Now we go to the application of this theorem. Application of this theorem. First application. Limit n tends to infinity n plus 1, n plus 2 to n to the power 1 by n. To find this limit, we can use this theorem. Here we take xn equal to n plus 1, n plus 2, n plus n, that is 2n by n to the power n. Then xn plus 1 equal to n plus 2, n plus 3, 2 into n plus 1, obviously 2n plus 1, and after that 2 into n plus 1 by n plus 1 to the power n plus 1. Now xn plus 1 by xn equal to xn plus 1 by xn equal to n to the power n by n plus 1 to the power n plus 1 into n plus 2, n plus 3, 2n plus 1, 2n plus 2 by n plus 1, n plus 2, n plus n. Here n plus 2, n plus 2, n plus 3, n plus 3, and this way here 2n cancel. Now n plus 1 and 2 into n plus 1 is also be cancelled. n to the power n by n plus 1 to the power n into 2n plus 1 into 2. Okay. Equal to. Here 1 n plus 1 left. Now 4 into 1 plus 1 by 2n by 1 plus 1 by n into 1 by 1 plus 1 by n whole to the power n tends to 4 by e, because this limit tends to e. This is very important limit of the sequence. So xn plus 1 by xn tends to 4 by e. So obviously xn to the power 1 by n tends to 4 by e by using Cauchy's second limit theorem. So we can say that this is xn, this is xn to the power 1 by n to the power 1 by n, 1 by n into n plus 1, n plus 2, 2n to the power 1 by n tends to 4 by n. Okay, this is the use of second limit theorem. Now go to the second application. Second application, limit n tends to infinity n by n factorial whole to the power 1 by n. This is the second application. Here we take xn equal to n to the power n by n factorial. Then xn plus 1 equal to n plus 1 to the power n plus 1 by n plus 1 factorial. Now xn plus 1 by xn equal to n plus 1 to the power n plus 1 by n plus 1 factorial into n factorial by n to the power n equal to n plus 1 by n to the power n, and n factorial cancel. Here left n plus 1 and n plus 1 cancel. So 1 plus 1 by n to the power n tends to e. So by Cauchy's second limit theorem, we say that limit n tends to infinity xn to the power 1 by n equal to e. That is, xn means this limit n tends to infinity n by n factorial to the power 1 by n equal to e. And this is the problem. So we see two application of Cauchy's second limit theorem and proof and the converse. Okay, thank you for watching and wish you have a nice day.